In this video, we're going to be talking about inequalities. So we're going to be making a shift away from equations and into these things called inequalities. So our essential questions are, what are inequalities? And what do solutions to inequalities look like on a number line? So first of all, what are inequalities? Now, inequalities are statements that compare two things that are not necessarily equal. This is what makes them different than equations. Equations state that two things are equal, and I give examples of those down below here. Here we can see that 10 equals 10, 2 plus 2 equals 4, 28 equals 7 times 4, and we've seen equations with variables x plus 8 is equal to 19. Those are all examples of comparing two things that are equal. Now, inequalities are different. They describe how two things that are not equal compare to one another. So if we look at these statements over here, we see 8 is less than 10. That's the less than symbol. That tells us that 8 is not equal to 10. It's less than 10. It tells us how it compares to it. Next one, 29 is greater than 10. Or negative 15 is less than 4, or we could even see variables included in our inequalities. X is greater than 9. So the big difference here is that we're comparing two things that are not necessarily equal to one another, and we're going to be using those symbols to indicate that. So here are the inequality symbols. A lot of students will forget these or confuse these, so these would be a great thing to have written down and memorized. The first one here is the less than symbol. And the less than symbol is an arrow pointing to the left, so you can think of left as less. Left is less. That means the value on the left is less than the value on the right. So that's how we would read that from left to right. The next symbol is the greater than symbol. That's an arrow pointing to the right. The value on the left is greater than the value on the right. And then here are a couple others that some students may have never seen or get confused. This is the less than or equal to symbol. So now we've got two options. The value on the left is less than the value on the right, or the value on the left is equal to the value on the right. If either one of those is true, then that statement, that inequality statement, is true. And then finally, we have the greater than or equal to symbol. Again, that means the value on the left is greater than the value on the right, or the value on the left is equal to the value on the right. So we've got a couple options there. So let's practice putting the correct symbols in here. We're going to use the correct inequality symbol to compare each pair of values. So here we want to compare 12 and 19. These are obviously not equal to each other, so we can't use an equal sign, but we will use an inequality sign or an inequality symbol. 12 is less than 19, so we need to use the less than symbol. That would be the correct way to compare those statements mathematically. 12 is less than 19. Next, we have 7/10 and 73/100. When it comes to decimal values, we get a lot of confusion sometimes, but when you're comparing decimal values, make sure you have the same number of place values. So here we both have out to the hundredths place, and now we can compare 70/100 and 73/100. Well, 70/100 is less than 73/100, so we put the less than symbol in there. And then also be careful when comparing negatives. Remember, the larger a negative value is actually further away from 0 or further left on the number line, so it is smaller. So negative 18 is actually greater than negative 20, so we put the greater than symbol in there. And then again, here's another case where students could get confused. One of these is repeating decimal, 0.3 repeating and 0.3. So again, if we were to write this value out underneath here so we can compare our place values, this is 0.3 repeating. So this is a bunch of 3's that go on and on and on. And this is just 0.3. So there's actually just an endless string of zeros after that. So when you write it out, you can see that these are equal, but these are not. The one on the bottom is actually greater. So 0.3 repeating is greater than 0.3. So a couple of cases there to be careful of when comparing values. Decimal values, negatives, and then when you've got repeating decimals, you might need to expand those and write them out to compare those. So here we are going to find some numbers that make each inequality statement true. So now we've got some variables involved. X has to be less than 10. So here I have a bunch of numbers, and all we have to do is pick the numbers that make that statement true. So basically, what values are less than 10? So if we go through this, is 5 less than 10? Yes, 5 would be a solution to that inequality. 5 would make that true. 9.9, is 9.9 less than 10? Yes, that makes it true. 12, is 12 less than 10? No, 12 is not less than 10. That would not be a solution or not a value of x. 10.0001, is that less than 10? No, it's ever so slightly greater, but it's still not less than 1/2. 1/2 is less than 10. Negative 19 is less than 10. 53 is not less than 10. And 10 is less than 10. Is 10 less than 10? No, 10 is not less than 10. 10 is equal to 10. So all of those would be possible solutions to that statement. Next one, G is greater than or equal to 19. 7, is 7 greater than or equal to 19? No. 19 and 1/3 is greater than or equal to 19. 18.98 is not greater than or equal to 19. 0 is not greater than or equal to 19. Negative 5.6 is not greater than or equal to 19. 19, is 19 greater than or equal to 19? It actually is. It's not greater than 19, but it is equal to. So now when we have this symbol, we have that option of being equal to as well. So 19 is a solution to this because 19 is equal to 19. And that's the inequality symbol that we have. 34.8 is greater than or equal to 19. And 199 is definitely greater than 19. Next, 43 is greater than n. Here's another case where middle schoolers will get messed up, is when our variable is on the right-hand side of our inequality. 43 is greater than n. So if we put 45 in for n, is 43 greater than 45? No. Is 43 greater than 40? Yes. Is 43 greater than 8? Yes. Is 43 greater than negative 10? Yes. Is 43 greater than 116? No. Is 43 greater than 56.4? No. Is 43 greater than 12? Yes. And is 43 greater than 87.555? No. So you can see there are a lot of solutions or possible numbers that would make these inequalities true. That's what separates them from equations. Now, equations only have one possible number that would make it true. And we solved a bunch of equations and we found that one number that makes it true. Well, with inequalities, there are actually an infinite number of numbers that would make each inequality true. So what we do sometimes is we express those solutions on a number line, or we show it or draw a picture of all the possible numbers, because there's no way you can list every number that makes it true. So for example, x is less than 10. Could we list every number that is less than 10? No, that's impossible. There are literally an infinite number of numbers that are less than 10. So we can just say anything less than 10, or we could show it on a graph. So that's our second essential question for this video, is how do we show these solutions, or all of these possible solutions to inequalities, on a number line? So what we can do here is show that we have everything that is less than 10, but not 10. So if x is less than 10, 10 is not a solution. Okay, 10 does not make this inequality true, but anything ever so slightly less than 10, like 9.999999, would make it true. So how do we show that on a number line? Well, what we do is we go to 10 on our number line, and since 10 is not a solution, I'm going to put an open circle on 10 to show that 10 is not a solution, and I want everything less than 10 but not 10. So the open circle shows me that 10 is not a possible solution here, but I want everything less than 10. So on my number line, which direction from 10 is less than 10? Well, it'd be everything to the left. So what I do is I just fill in my number line and draw an arrow showing that all of these numbers to the left of 10, but not equal to 10, are solutions. So any of these numbers here in this purple region would make this true. So 5, for example, 5 is less than 10, 0 is less than 10, 1 is less than 10, 2 is less than 10. All of these numbers to the left of 10 would be a solution to that inequality. And then likewise, anything to the right of 10 would not be a solution. So 10 is not a solution. That's why that's an open circle. 11 is not less than 10. 12 is not less than 10. So that's kind of the cutoff here, or the border between true statements and false statements. And that's how we show that on the number line. So if we look at the next one, x is greater than 10. So here we want everything greater than 10, but not 10. Again, it has to be greater than 10. It cannot be 10. So I'm going to use an open circle again on 10, not on 9, not on 9.99 or 11.1 or 10.11, just on 10. Open circle on 10 because it could be 10.000000001 and still be true. So I can't put a dot infinitely close to 10. I just put an open circle on 10 to show that 10 is the cutoff, but 10 is not included. So open circle means that that value is not included. But everything greater than 10 would be to the right this time. So everything to the right of 10 is a solution. So we would just fill in our number line here, draw a nice thick arrow showing to the right of 10. So everything that's in the blue region would make this true. So 11 is greater than 10, 12 is greater than 10, and so on. And then everything to the left of 10 would not make that true. So when we have the less than symbol or the greater than symbol, we're going to be using an open circle on that dot because it's not included. Now let's compare these two statements. X is less than or equal to 10. So that means everything less than 10, including 10. Now 10 is a possible solution. So I'm going to put in a solid dot or a filled in circle on 10. Now 10 is included, and then I want everything less than 10, including 10. So again, I'm going to draw everything to the left on my number line, everything less than 10, including 10. So look at how that compares to the X is less than 10 graph. Here it's almost identical, but one has a filled in circle and one does not. That's the difference between the less than graph and the less than or equal to graph. We're going to include a filled in circle when it's or equal to. Likewise here, 10 or X is greater than or equal to 10. So again, 10 is included. We want everything greater than 10, including 10. So now I'm going to include 10 by putting a solid circle or a solid dot on 10, and I want everything greater than 10 as well. So I'm going to shade to the right and show everything greater than 10, including 10. So see how that compares to the graph of X is greater than 10. Again, almost identical graphs, except one has an open dot and one has a filled in dot. And that's the major difference there. So something to include in your notes, when you have these or equal to symbols, you're going to have a filled in dot. If you don't have or equal to, you're going to have an open dot on your graphs. Okay, so let's practice that here. Let's show these solutions on the number line. K is greater than -6. So when I'm creating a number line from scratch, it really doesn't matter what I include on my number line. I don't have to have every number from 0 to that number. But here's what I would like to see. I would like to see actually that number, the -6, because that's where the cutoff is going to be, and then include a few numbers to the right and a few numbers to the left. Don't just put -6 on the graph and call it good. And then actually label these. This would be -7, -8, -9. Just kind of give the viewer an idea of where you're at on the number lines. Okay, this gives me a good idea of where I'm at on the number line and gives me some idea of scale. So don't get lazy on your number lines. And then K is greater than -6. So it's everything greater than -6, but not including -6. So I'm going to put an open circle on -6 and then everything to the right. So everything to the right of -6 on the number line would make this true. And then what I would do is just pick a number in this red region, like -4, and see if that works. Is -4 greater than -6? Yes, that's true. Well, let's test one to the left of -6. Is -7 greater than -6? No, it's not. So I know that my graph makes sense, and it doesn't take long to double check that. Next one, M is less than 29. So again, I'm going to include 29 on my graph, put that in the middle, but then I'm going to include a few values to the right, 30, 31, and a few values to the left, just to give the viewer an idea of where I'm at on the number line and give me an idea of scale. So again, we're less than 29. So everything that is less than 29, not including 29, because 29 would not be a solution, but it is the cutoff. And then everything less than 29. So that would be everything to the left on the number line. And then again, if I just check one of these values, like 27, 27 is less than 29, that's true. And then if I test one to the right of it, 30 is not less than 29. So I know my graph makes sense. Next one, N is less than or equal to 8.7. So now I've got a decimal value. So to do that, I'm not really going to be counting by ones now. Now I need to get those decimal values in there. So I'm going to start at 8.5, and I'm going to count by 1/10. So this would be 8.6, 8.7, 8.8, 8.9, and 9.0. That would be enough to give me scale and scope, but to see where I'm at on this number line. So when I'm dealing with decimals, I might not be counting by ones, I might be counting by tenths or so on. So we want everything that is less than or equal to 8.7. So now 8.7 is included as a possible solution. So I'm going to put a nice solid dot on 8.7, and I want everything less than 8.7. So I'm going to go to the left, because these are all the numbers that are less than 8.7. And that's what the graph of that inequality would look like. And then lastly down here, f is greater than or equal to 4 2/3. So again, I've got a mixed number. So again, I'm probably not going to be counting by ones on my graph here. I'm going to go 4, and then I'm going to count by thirds, since that's what we're dealing with here. She's 1/3, 2/3, and then there would be 5. So this is 4 1/3. This would be 4 2/3, and then 5. That's enough on my number line to show me where I'm at. Just don't put 4 2/3 on your number line and that's it. Please include numbers to the right and numbers to the left so you can, again, get some kind of reference to where you're at on the number line and what each tick mark represents. And then we're at 4 2/3, and it is included because it's or equal to. So 4 2/3 is a possible solution to that inequality, and it's everything that is greater than 4 2/3. So I would draw my arrow to the right on the number line to show that that is those are all the solutions. So 5, for example, is greater than or equal to 4 2/3, but 4 is not. So that graph does make sense there. Now we're going to go the other direction. Here I'm going to give a graph, and then we want to write an inequality that matches that graph. So when I'm looking at this graph here, this is 4, 3, 2, 1, 0. So my dot is filled in and on 3. That means 3 is included, and it's the cutoff. And it's everything that is greater than 3 or equal to 3. So I could write an inequality like x is greater than or equal to 3. That's everything that is greater than 3 or equal to 3. Next one here, here is 0. So that means this is -1, this is -2, -3, -4. So to fill in those values there. So my dot is at -1. So that's where the values cut off. And it's everything that is less than -1, but not including -1. So x is less than, but not equal to, -1. So x is just less than -1. That would be the inequality that that graph shows. And then lastly here, we've got 8, 9, and 10. So these values right here, we're kind of 1, 2, 3, 4. These are all fourths. So that means this is 8 1/4. This is 8 2/4, which is 8.5. And this is 8 3/4, and then 9. So that gives me kind of the scope of where I'm at here. That's why we include more than one number on our number line to show what we're counting by. So it's 8 3/4. So x is going to be greater than 8 3/4, but not equal to, since that's an open dot, x has to be greater than 8 3/4, but not equal to. So x is greater than 8 3/4. That's what that graph shows. So inequalities, they are statements that compare things that are not necessarily equal, and graphing them on the number line. Open circles when you have greater than or less than, filled in circles when you have less than or equal to or greater than or equal to.